This is my next high voltage probe. This is made out of 3 different shell cases. There's a 223, a 35, and a 2506. These have just been soldered together. This is a completed one. These are just Everett Charles pogo pins. See, the end just fits off. There's a connector in the center here. Fairly small. You can see it fits nice in the palm of your hand. Cheap. I'm using standard coax with these. Results are not as good as my burrito probe, but certainly good enough for the work that I would be using them for. Again, this one's fully assembled. The second one here is still in pieces, and I'm going to go ahead and run this unit, and then I'm going to take it apart and show you how it's constructed. Here the probe's attached to the network analyzer. Again, I'm just using the BNC adapter. The output from the probe is just attached to the input of the DSO. This is currently looking at 350, about 360 megahertz. And we can see here the tip capacitance is roughly called 11 picofarads. So 11 picofarads at 350. It's a little higher capacitance than what this LaCroix probe had on it, but we're in the ballpark. Right now the input to the probe is just connected to a 33120A. It's an Agilent ARB. You can see the output of the waveform. This is a 1 Hertz signal. And currently the ARB is putting out 2 volts peak to peak. So you can see it's 500 millivolts per division right now, or roughly 2 volts. This is the waveform at 10 Hertz. This is at 100 Hertz. This is 100 kilohertz. And this is 15 megahertz. The generator doesn't produce square waves very well up at this frequency. So what we'll do is we're going to connect this up to an RF generator. This is 114 meg. This is 57 meg. Three meg. This is a 447 kilohertz. So the response isn't too bad. It's definitely usable. See, I use a standard end style connector on this pulsar drive. So I had made this adapter. It just goes from a standard end. It's got some copper here that pushes up against the lips of the probe. Yeah, unfortunately the shell cases are not the standard sizes for like the 5100 Tech probe. So here I've got the probe connected to our high voltage pulsar. You can see the probe isn't soldered together right now. It's actually doing pretty good. I'm surprised it's making this good a contact. There's a little jar. I don't know if you saw that or not, but yeah, until I solder the whole assembly together, it's going to be prone to noise. You can see on this one here, I've actually soldered around the lip. This probe won't come apart ever again. I wanted to make this video while I was still working on assembling the second one, just to give you an idea how it was assembled. It's at 500 volts per division. Here you're looking at 1000 volts. This is currently at 10 hertz. This is 30 kilohertz here at roughly 1 kilovolt. So again, this is 500 volts per division. I'm just adjusting the output from the two power supplies that are driving the pulsar. Again, the probe's got no issues with this. The response really looks pretty good. Give you an idea here. Here we're looking at 50 nanoseconds per division. Or roughly, the rise time is roughly 66 nanoseconds. That is pretty much the limit of what this pulsar can put out. I've measured this pulsar using a real scope probe, not these handmade ones, and get roughly the same rise time. Again, the ringing here is a result of my compensation and using this coax, but for me, again, it's very acceptable. We've got our dummy load again hooked to our amplifier. Again, just a cobbled up bracket here to get the scope probe sort of mounted into the BNC jack. So the output of the amplifier again just going up to our load. Currently the RF generator is set to 52 megahertz. And again, the probe is just connected to the one channel of the oscilloscope. This is 20 volts per division right now. That's into a 50 ohm load. What I'm going to do is turn up some power here. So you're looking at 80 volts peak to peak. Scope says 83. There's 100 and there's 150 volts. This is now 50 volts per division. It's about the limit of the amplifier right there. So it's currently 166 volts. It's dissipating quite a bit of power here. We'll just let it sit here and cook for a little bit. The P4100 couldn't survive this test. I was running 100 volts across it when it gave out. That was basically what that probe was rated for. This probe, on the other hand, will handle this kind of power and without any issues. Yeah, our heatsink is not keeping up very well. It's a lot of power to be dissipating. So the RF generator is now set for 100 megahertz. Then this is driving the same power amplifier. The main power amplifier is now connected up to our secondary amp. And again, our probe is just tapped to the T. And the output of the other side of the T is just going to our 50 ohm load. So currently, we're putting out about, scope saying about 34 volts here. This is roughly 100 volts at 104 megahertz. It's about 150 volts now. And we're putting out a fair amount of power here. Yeah, it looks pretty good. It's 200 volts there, 100 volts per division, 200 volts peak to peak, again at 100 megahertz. This is about the limit of the amplifiers. It's about double what I had the 4100 at when it melted. You have to let things cool down here a little bit. So while the system's cooling here, let me just show you what's inside of this. So again, the tip is just machined out of Teflon. Here you can see the connector for the pin. This is just standard Ever Charles parts. They're like a bed of nails tester. It's kind of nice, you can put whatever kind of probe tip in here you want. So inside of the tube here, there's a sheet of Teflon that I spooled up. I slid it into the tube and then I let it expand. So that actually has quite a bit of gap in here between the walls of this and the probe. So up here we can see the connector. Below this there's a small resistor. This is the 100 meg resistor here. These two pieces of magnet wire have Teflon over the top. These are actually the capacitor. This is where all the time is spent, right here. Next down here is a piece of ferrite, and then into the BNC. Fairly simple construction. Again, this resistor here, this is rated for 10,000 volts. The low voltages we're running at, this probe will have a very long life. Let's see here, the Teflon skirts just slide off. You can see here how the magnet wires loop back on itself. The sheathing actually runs quite a bit farther up just to prevent a breakdown. Again, I had this sitting at 2 kV. I don't plan to ever run it up that high, but had it sitting at 2 kV all day with the other probe, no issues at all. So that's what my cheap probe looks like.